Kepler's third law. I'm going to start by just writing out mt squared over r cubed equals 1. As long as mass is in solar masses, time is in years, and r is in astronomical units, this is true. So it's solar masses, years squared, astronomical units cubed. The value of G is Newton meters squared per kilogram squared, and a Newton is a kilogram meter per second squared. So I will just multiply that by meters squared per kilogram squared, and you'll find that this also has units of meters cubed over seconds squared times kilograms. So actually, what I'm going to do is say that there is actually another factor, mt squared. No, mt squared. Let me write it the other way. So we get r cubed over mt squared equals g. Now the units match up, and there's just another factor in here of 4 pi squared. And this is in SI units. So you can use SI units, or you can use solar masses, years, and astronomical units. And actually, I should have said equals 1 AU cubed over 1 mass of the sun squared, times years squared. And G over 4 pi squared comes out to be 1.69 times 10 to the negative 12th meters cubed over seconds squared kilograms, or 1 astronomical unit mass of the sun squared years cubed. No, mass of the sun years squared. So you can be given any large central mass and the distance that a very small mass is from it, and from that equation calculate how long it will take to go around, or vice versa. If you're given how long it takes to go around, you can find out how far it is from the mass. Another topic about Kepler's laws is that things like planets, most of them have very, very small eccentricities and go around the sun in very close to a circle, and that radius is called r. Now, a comet, such as Halley's Comet, goes close to the sun for a little bit, and then it goes out and it forms something called an ellipse. And an ellipse is a particular form of geometric form. It's actually a conic section. If you take a cone and split it like along a plane like that, what you get out of it is an ellipse, the cross-sectional area. And the cone has a couple of features to it. There's a point over here called a focus, and that focus is where, say, the sun might be, and as the comet goes around, it goes around the focus. And there is the apogee and the perigee. This is the apogee, I think, and this is the perigee, the closest approach and the farthest approach. And anyway, this distance here is called 2a. It's 2 times the semi-major axis, where the major axis is, of course, the whole thing. And it turns out that if you use half of this distance, um, then you can basically still use this equation here and just put the semi-major axis in here for r. Or sorry, this equation here, you can just put the semi-major axis in for r. And it's also interesting, while I'm talking about the conic section, if I put a point right there at the center of that ellipse and draw other ellipses that are parallel to it, and then draw a line through the center, you can draw a line through the center of all of those ellipses. And this is kind of a key notion in special relativity, that no matter what line I draw through a cone like that, I can always find a set of ellipses or circles that line will be the center. And they do this with something called a space-time diagram, where this is space and this is time. Okay, I'm getting way off topic here. Okay, sorry about that. Okay, example 7.13. From a telecommunications point of view, it's advantageous for satellites to remain at the same location relative to a location on Earth. This can only occur if the satellite's orbital period is the same as the Earth's period of rotation, approximately 24 hours. We want to find the distance from the center of the Earth that this geosynchronous orbit can be found, and what is the orbital speed of the satellite. So I'm going to use this form of the equation, and we want to find r. So we'll go ahead and multiply gmt squared over 4 pi squared. Gravitational constant is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And here's the trick to it. We need t, the period, to be 1 day. So we'll take 24 hours times 3,600 seconds per hour. Let's do that like that. And then we will square that, divide by 4 pi squared. And then, since this is r cubed, we will take that whole thing to the power of 1 over 3. And this comes out to be 42.3 million meters. Quite a long distance. Part B asks for what is the orbital period. Now the orbital period is 24 hours. Actually, part B asks for what is the orbital speed. And the speed, v, is equal to s, or r times omega, which is r times 2 pi over the period. 42.6 times 10 to the 6th times 2 pi over 24 times 3600. Which comes out to be somewhere around 3100 meters per second. Question 7.13. If the satellite was placed in an orbit 3 times as far away, about how long would it take to orbit the Earth once? Answer in days, rounding to 1 digit. So let's look at it like this. R cubed over mt squared. And we are going to, what did they say? We're going to place it 3 times as far away? 3 times as far away and orbiting the Earth once. So we want to solve for time. So this was 1 day at, and we want to solve for time. T squared equals r cubed over m, and basically we're going to have the same mass, and we're going to triple the radius. So 3. So yeah, we'll just make it so t equals 3 cubed to the 1/2. So that is square root of 27, which is 5.196, but they want it rounded to just one significant digit, so it's 5 days. Got 3 times as far, and it takes 5 times as long to orbit.